this ancient engineering trick still outperforms modern designs. From the Colosseum in Rome to the aqueducts of ancient Greece, history is filled with structures that have baffled engineers for centuries. Many of these feats continue to inspire modern architecture, not just for their beauty, but for their remarkable durability. While today's engineers rely on high-tech materials, computer models, and precise simulations, some ancient techniques remain surprisingly more effective, even when compared to modern designs. One particular engineering trick, used across civilizations, continues to outperform modern methods in ways that are subtle, yet profoundly practical. Understanding it requires looking at how ancient builders thought, not just what they built. Ancient arches are the perfect starting point. The Romans mastered the use of arches in bridges, aqueducts, and buildings. Unlike modern beams, which rely heavily on material strength, arches distribute weight along curved lines, transferring stress to the supports at either end. This allows for large spans using relatively modest materials. Modern engineers can replicate this principle with steel or reinforced concrete, but the precision and elegance of ancient arches are still remarkable. Bridges built almost 2,000 years ago still carry weight daily without significant repairs. The trick lies not in the materials themselves, but in how forces move naturally along curves, a principle sometimes overlooked in modern straight-line thinking. The Pantheon in Rome provides another example. Its dome remains the largest unreinforced concrete dome in the world, nearly 2,000 years after it was built. Modern concrete relies on steel reinforcement for structural integrity, yet the Pantheon achieves stability through clever layering and density variations in its materials. Lighter volcanic pumice was used near the top, while denser aggregates supported the base. This method reduced weight without sacrificing strength. Engineers today might achieve the same results using sophisticated composites or reinforcement, but few modern domes combine such efficiency with simplicity. The ancient approach illustrates a principle modern designers are only beginning to fully appreciate. Engineering solutions can leverage material properties and geometry rather than brute force. Water management systems further reveal this ancient ingenuity. Roman aqueducts, qanats in Persia, and step wells in India all demonstrate sophisticated control over water without pumps or modern machinery. Gradients were calculated with incredible precision, often less than a few centimeters per kilometer, allowing water to flow smoothly over long distances. Modern pumping systems require electricity and maintenance, yet many ancient aqueducts functioned reliably for centuries with minimal upkeep. The design principles, gravity, slope, and careful material choice remain relevant today, especially in sustainable engineering, because they reduce dependence on external energy and minimize mechanical failure points. Even in earthquake-prone regions, ancient methods outperform expectations. Japanese pagodas, built centuries ago, survive earthquakes that destroy newer concrete structures. Their flexibility, distributed weight, and interlocking wooden frameworks absorb seismic energy instead of resisting it rigidly. Modern buildings often prioritize stiffness and high-tech dampening systems, but pagodas demonstrate that allowing a structure to move with natural forces can outperform rigid modern designs. The principle is counterintuitive. Instead of trying to fight nature, ancient builders allowed it to work with the structure. Modern engineers increasingly adopt similar strategies, but the ancient approach still serves as the benchmark for resilience in low-tech, sustainable ways. Bridges in the Inca Empire reveal yet another ancient trick. Many Inca stone bridges, especially in the Andes, were dry-laid, meaning no mortar was used. Stones were shaped precisely to interlock, creating compressive strength that allowed the bridges to survive centuries of use and occasional earthquakes. Modern bridges rely heavily on concrete, steel, and exact calculations, yet these Inca constructions combined local materials, topography, and intelligent design to achieve durability without high-tech interventions. The concept is simple but profound. When materials and geometry are harmonized, performance exceeds expectations even centuries later. Domed structures in the Middle East offer another lesson. Ancient Islamic architecture, from mosques to palaces, often employed a technique called the double-shell dome. The inner layer provided structural support, while the outer shell maintained aesthetics and reduced weight. This design is remarkably similar to modern engineering solutions in stadiums and large arenas, where a double-layered roof or cladding distributes weight while reducing material stress. Yet the ancient builders achieved this without CAD software or steel reinforcements, relying instead on empirical knowledge, careful observation, and incremental adjustments passed down through generations. The ingenuity lies in simplicity married to precise execution, a combination still rare in contemporary projects. Even roads and foundations reveal ancient tricks still superior in some ways. Roman roads, for instance, were layered with stones, sand, and gravel in a way that allowed drainage, prevented erosion, and distributed weight efficiently. Modern asphalt roads can fail due to water penetration, temperature changes, or material fatigue, whereas Roman road sections survive intact after millennia. The principle is clear. Layering with different densities and permeabilities creates durability far beyond what a single uniform material can provide. Engineers today sometimes overlook these natural design lessons in favor of chemically engineered solutions that may last decades, but rarely centuries. Concrete itself, as used in antiquity, has secrets modern scientists are still uncovering. Roman concrete, for example, gains strength over time when exposed to water, especially seawater. Unlike modern Portland cement, which can degrade over decades, ancient concrete reacts with volcanic ash and lime to form mineral bonds that reinforce the structure indefinitely. Harbors built during the Roman Empire still survive in marine environments where modern concrete would crumble. The lesson is that longevity is not merely a function of initial strength, but chemical compatibility with the environment. Ancient engineers understood this intuitively. Modern engineers are only now rediscovering it through research and experimentation. City planning itself reflects a deep understanding of environmental and social factors. Ancient cities often incorporated natural ventilation, water management, and sun orientation long before modern computational fluid dynamics existed. Streets, courtyards, and building orientations were designed to maximize airflow and natural cooling. Today, engineers rely on HVAC systems and technology to achieve similar outcomes. Yet ancient cities achieved comfort and efficiency passively, without energy consumption. These urban principles can inform modern sustainable architecture, demonstrating that old designs still outperform in terms of resource efficiency and adaptability. The takeaway is clear. Ancient engineering tricks are not obsolete. They are living lessons in how humans can work with natural forces, materials, and topography to create solutions that endure. When combined with modern tools, these ancient principles offer a roadmap for sustainable design, long-lasting infrastructure, and resilience in environments that challenge contemporary construction. Studying these techniques expands both imagination and practicality, showing that sometimes the old ways outperform the new. Not because they lack sophistication, but because they embrace principles that remain universally effective. If this exploration of ancient engineering's hidden advantages inspires curiosity, take a moment to like this video, subscribe for more in-depth explorations of technology and history, and share it with someone who believes modern methods are always superior. There is always another ancient technique, another structural principle, another insight waiting to challenge assumptions about what we consider advanced. History is not only a record of the past, it is a guide for smarter, stronger, and more resilient design today.